Before recording this lecture, I stopped by in a coffee shop. This cappuccino is good. And as soon as I gave $5 to the cashier, she faced an algorithmic problem with which coins to select to give me the change. And cashiers all over the world use an algorithmic approach called greedy algorithms to solve this problem. Today, we will learn how cashiers and computer scientists use greedy algorithms for solving many practical problems. So the change problem is finding the minimum number of coins needed to make change. More formally, input for the problem is an integer money and positive integers coin 1, coin 2, coin D that represents coin denominations. For example, in the US, coin 1 will be 1 cent, coin 2 will be 5 cents, 10 cents, 25 cents, and 50 cents. And the output is the minimum number of coins with its denominations coin 1, coin 2, coin D that changes money exactly. So today in the morning, when cashier had to return me 40 cents, she most likely used the following algorithm. First, finding the largest coin denomination that is smaller than 40 cents. It will be 25 cents. So she gave me 25, 15 cents left, and then the next challenge is how to change 15 cents. The next step is she probably found the largest coin smaller than 15 cents. It is 10 cents. She gave me 10 cents, and finally she returned 5 cents. As a result, she changed 40 cents as 25 plus 10 plus 5. Do you think it's the minimum number of coins she could possibly return? It is the minimum number of coins in the United States. But if you travel to Tanzania, it won't be the minimum number of coins because there is a 20 cents coin in Tanzania. And therefore, this greedy approach to solving the change problem will fail in Tanzania because there is a better way to change 40 cents, simply as 20 cents plus 20 cents, using Tanzanian 20 cents coin. Since the greedy approach to solving the change problem failed, let's try something different. Let's try the recursive algorithm for solving the same problem. Suppose we want to change 9 cents and our denominations are 1 cent, 5 cents, and 6 cents. What would be the optimal way to change 9 cents? Well, if we only knew what are the optimal ways to change 9 minus 6 cents, 9 minus 5 cents, and 9 minus 1 cent, then we would know what is the optimal way to change 9 cents. Or in other words, to change 9 cents, we need to know how to change smaller number of cents, in our case 3 cents, 4 cents, and 8 cents. And therefore, an approach to solving this problem would be to use this recurrence to write the recursive program. This idea is implemented in the program recursive change. To change money cents using coins coin 1, coin 2, coin D, we do the following. We first recursively call recursive change with the amount of money minus coin 1, money minus coin 2, and money minus coin D, and find the minimum amount of money for these D choices. We add plus 1 because there is one more coin to add and return this value. This looks like the right approach to solve the problem, but let's check how fast the resulting program is. So when we're changing 76 coins, there are actually 3 choices. We need to recursively call recursive change for 70 cents, 71 cents, and 75 cents. But for each of these values, we need once again to call 3 choices. And we will continue growing this tree, and very quickly it will turn into a gigantic tree. Let's check how many times we have already tried to change 70 cents. 3 times, and we only started expanding this tree. In fact, if we continue further, we will see that there were 6 times when we needed to compute recursive change for 70. How many times do you think we will need to run recursive calls when we compute the minimum number of coins for 30 cents? It turns out that we will need to call it trillions of times, which means that our seemingly very elegant recursive change program will not finish before the end of your lifetime. So as simple as the change problem looks like, neither greedy approach nor the recursive approach solve it in a reasonable time. 60 years ago, a brilliant mathematician, Richard Bellman, had a different idea. Wouldn't it be nice to know all the answers for changing money minus coin I by the time we need to compute an optimal way of changing money? And instead of the time-consuming calls to recursive change money minus coin I that may require to be repeated trillions of times, we would simply look up these values. This idea resulted in dynamic programming approach that is applied in thousands of diverse practical applications in a myriad of different fields. And the key idea of dynamic programming is to start filling this matrix not from the right to the left, as we did before in the recursive change, but instead from the left to the right. So we will first ask the trivial question, what is the minimum number of coins needed to change 0 cents? And of course it is 0. What is the minimum number of coins to change 1 cent? Obviously it is 1, but we can compute this number by finding what is the minimum number of coins to change 0 cents and adding 1 coin. We will proceed in a similar fashion to compute the minimum number of coins to change 2 cents, 3 cents, and 4 cents. There is only one possibility to derive this number from the previous number, and for 5 cents, actually there are 2 possibilities, green and blue. For green one, you can derive it from 0 cents by adding 5 coin, and for blue possibility, we can derive it from 4 cents by adding 1 penny. Which possibility would you select? Of course, the one that gives you the minimum change for 5 coins. We can continue further and applying it to 6 cents. There are now 3 possibilities, and once again we select the optimal choice that corresponds to minimum number of coins. Let's say it may be 0 coins plus 6 cents. We continue for 7 cents, continue for 8 cents, and finally, very quickly, we actually found the correct answer for 9 cents. We need 4 coins to change 9 cents. And it results in DP change algorithm that simply fills up the table that I just showed you from left to right. DP change is the first dynamic programming algorithm that you saw in this course, and there will be thousands more. You may be wondering why this algorithm called dynamic programming and what it has to do with programming. Well, in fact, programming in dynamic programming has nothing to do with programming. Amazingly enough, dynamic programming is one of the most practical algorithms computer scientists use. But when Richard Bellman was developing this idea for Air Force project he was working on, it looked completely impractical. And he wanted to hide that he is really doing mathematics from the Secretary of Defense rather than working on Air Force project. Therefore, he invented a name that basically has nothing to do with what dynamic programming algorithms do. In his own word, he said, what name could I choose? I was interested in planning, but planning is not a good word for various reasons. I decided, therefore, to use the word programming, and I wanted to get across the idea that this was dynamic. It was something not even a congressman could object